Hello everyone, my name is Zhaoxing, come from Kyoto University. Today I'm going to talk about the SRAM-based Scratchpad memory for organic IoT sensors. The organic thin film transistors is like this. It is the top contact backgate structure, and the materials of the N-type is the TU1, and the P-type is the DNTT. It is the flexible device and can be driven by low voltage, such as 3 volt, and it can be fabricated by low cost and low temperature process. And now it is expected to utilize in various applications such as flexible sensors, processors, RFID tags, and so on. As these applications develop, there's also demand for the local data storage. If we can store data locally, we can save the transmitting power and time. And if the whole system can be fabricated in the same process, it can also decrease the fabrication cost. Therefore, our objective is to design memory for the organic applications, and in this work, we choose SRAM as the memory. The proposed memory is suitable for the unipolar OTFTs, and it can also against the device degradation. And this is our proposed memory architecture. It is based on the SRAM architecture with a SRAM array, a row and column decoder, a sense amplifier for the data readout. And here we added a mitigation circuit to the device degradation, and I will introduce it one by one. The proposed OTFT memory cells is shown in this. For a stable operation, the constraint for the device is like this. The P-type pull-up transistors should be stronger than the P-type oxide transistors and stronger than M-type pull-down transistors, which is different from the traditional SRAM constraint. And this one is suitable for the characteristics of the OTFTs, and it can gain higher stability and air efficiency. In our proposed memory cell, the access transistors are changed from N-type to the P-type and with zero pre-charge before reading. Through this construction, we can change the traditional constraint of the device. And next, we use the differential amplifier as a sense amplifier. And in this work, the N-type current mirror load is utilized to obtain higher gain. And next, I will talk about the device degradation. The weak pull-down N-type is easily to degrade it because of the bias stress. As the degradation becomes severe, it may cause the change of the stored value, such as from 0 to 1. Therefore, we propose the mitigation topology is that we can occasionally flipping the stored value. Here, we take the VTH, threshold voltage of the device as an example, and this is a simple simulation result of the VTH. If we don't flip in the node voltage constantly biased, the VTH will get higher and higher. But with our proposed topology, flipping the node voltage, the VTH will have a periodically process like the degradation, recovery, like that. And from the results, we can see that the whole degradation can be mitigated a lot through our proposed topology. And next is our experimental result. In this work, we implement a 4x4 SRAM array to confirm its operation. And this is our static noise margin of one cell. This results indicates that our proposed cell can operate stable. And the read and write operation of one cell is shown in this. We can see that the signal written before can be read successfully after the word line turns on, and the sense amplifier can also work correctly. The read time can be accelerated by 50% by the sense amplifier. And next is the operation of a select row. In the write phase, we write 1010 into a row, and in the read phase, the 1010, all the signals written before can be read correctly. And this indicates that our SRAM array can work correctly. And finally, we confirm the effectiveness of the mitigation topology for the degradation. We plug the voltage of 0 and 1 level in the stored value. We can see that if we do nothing, the 0 level will get higher and higher and finally flip at about 5 hours. But with our proposed topology, the 0 level is almost not changed and can be maintained for at least 8 hours. And this is our works. Thank you for your listening.